Welcome to the pre-lecture for Class 20, where we will be talking about nonlinear systems and phase plane analysis. That's how we are going to be wrapping up the semester. The nonlinear differential equations that we are going to be looking at typically cannot be solved analytically. So we are going to be relying on some other methods of analysis, including looking at phase portraits, doing some local stability analysis, and numerically computing solutions. We do get to see a lot of interesting phenomena that are only possible when we have nonlinear systems. Some interesting examples can be seen at these YouTube links, and I will leave you to take a look at those yourself. Let's go to the next page. So in order to start talking about these nonlinear systems, let's make sure that we are on the same page when it comes to notation. The most general way to write a linear system of first-order differential equations with constant coefficients is like this. In the case of a homogeneous system, the zero vector is always going to be a solution. The next most general linear system is one where the matrix has possibly time-dependent coefficients and there is a forcing function. That's system 2. The forcing function is going to be a vector of possibly time-dependent entries, and the matrix is n by n and possibly also has time-dependent entries. Finally, the most general nonlinear system of equations can be written like this. Note that if our function f, our right-hand side, does not depend explicitly on t, then our system is autonomous. If we were to write out this system as individual equations, it would look something like this. Let's go to the next page. Here we have a reminder of the kinds of models we have already seen. Pause briefly and try to write each of these ODE systems in matrix vector form if possible. If the system is linear, you can always write it in matrix vector form, but if it's nonlinear, just write it as a vector. Our first system is linear, and the function f is going to determine whether or not it is autonomous or driven. Since the system is linear, we can write it as matrix vector equations. Next, our chemical reaction system is nonlinear and autonomous. Since it's nonlinear, we can't write it as a matrix vector multiplication. We can simply write it as a vector. The remaining systems, the SIR model and the swinging pendulum, are also nonlinear autonomous systems, and therefore also both of them have to be written simply as vector equations. Note, by the way, that when you look at these systems, it should become clear why our nonlinear systems don't get categorized as driven or non-driven, whereas it makes sense in the context of a linear system because we can easily separate out the matrix vector multiplication from the driving term. Let's go to the next page. As with each generalization we have made to the kinds of systems of differential equations we look at, we have to remind ourselves of the existence and uniqueness theorems that we have available to us. Now, in the case that we're dealing with potentially nonlinear systems of equations, we return to an extension of what we saw when we looked at a single nonlinear ODE. When we had a nonlinear single ODE, we required that the right-hand side f and its partial derivative with respect to space were both continuous. Now, when we look at existence and uniqueness for the system, we have something similar. Each entry of our vector function f and the space derivative of each entry must be continuous in some box B in n+1 dimensional space. When we have that, then there will exist a solution to the initial value problem on some time interval that contains our initial point t0, and the solution will be unique. In 2 space dimensions, we have a 3-dimensional curve. A corollary to our existence and uniqueness theorem says that under the same continuity conditions as we have above for the autonomous system of differential equations, solution trajectories will not intersect in phase space. The proof of that, as we've seen before, is by contradiction. If 2 solution trajectories were to cross in phase space, even if they crossed at different times, that would lead to a contradiction, because imagine if we considered starting our initial value problem from that particular point where a crossing happens. Those different trajectories would imply multiple solutions to the initial value problem, which is not possible. Let's go to the next page.
Here we introduce some useful vocabulary.
We've made mention of the phase space. So the phase space for system of differential equations is a coordinate space where all the dependent variables are the axes. If there are only two dependent variables, then we have the phase plane. So for example, with two dependent variables, we simply will be plotting our trajectories in, say, the XY plane. These dependent variables are also called state variables. Notice again that in phase space, time t is not seen explicitly. A direction field for an autonomous system of differential equations is going to be a vector field plot of f, the right-hand side, in phase space. In 2D on the phase plane, we can plot the slope f at each point x. Note, by the way, that the reason we don't plot the direction field for a non-autonomous system is that the direction field is going to change with time. Another term that's important to get familiar with is that of orbits, or trajectories, or solution curves. These are actually three names for the same thing. These are the solutions to the differential equations plotted in phase space parametrically with time t. Now, for a planar system in 2D, that is, the concept of nullines is important. The x nullline is going to be the set of points xy such that x prime is 0. In other words, it's the collection of points along which there is no left-right movement, no movement in the x direction. Similarly, the y nullline is the set of points where y prime is 0. So there will be no up-down movement, no movement in the y direction. We can generalize this concept to any autonomous system of ODEs where each dependent variable or each state will have its own set of nullines. Note, by the way, that the nullines usually separate portions of space where the solution curves either have the state space derivative positive or the state space derivative negative. The equilibrium points are all going to exist at the intersection of all the nullines. So, for example, with n states, then we need to find where all n nullines intersect in order to have an equilibrium point. Now, it turns out there is a very standard process for carrying out a qualitative analysis of nonlinear systems that involves sketching the phase portrait. And that process is as follows. You first find and plot all the nullines. Then the places where all the nullines intersect are going to be the equilibrium points. Identify where they are. And then finally, we can determine the direction of solution flow by looking at the sign of the ODEs in regions between the nullines. Let's go to the next page and see how that might look. Here we have the qualitative analysis process sketched out again. Find all the nullines, plot them, find the equilibrium points, and then determine the direction of solution flow, from which we should be able to infer what the phase portrait curves might possibly look like. Let's look at this example. And let's do step 1, finding and plotting the nullines. The x nullline is found by using equation A. So the x nullline is simply the line y equals 0, which is just the x-axis. We can find the y nullline by using equation B. This gives the equation for the curve 1 minus x squared. Note, by the way, that for the sake of plotting, whether we are looking at the x nullline or the y nullline, it is often convenient to write the equations in terms of y equals some function of x, if possible. Now, from here, we actually could compute all the equilibrium points. It's fairly apparent that we will have 2 of them, and they will be at -1, 0 and 1, 0. But let's first plot these nullines. Remember, our first nullline was y equals 0, and so I will highlight the x-axis. The y nullline was given by the curve 1 minus x squared. That'll look something like this. Notice that when I look at the intersections of the x nullline and the y nullline, those are exactly the points we predicted, -1, 0 and 1, 0. The final step is to determine the direction of solution flow by looking at the sign of the ODEs in the regions between the nullines. So for convenience, let me write down the ODEs up in the left corner so we can reference those. Let's look first in the regions both above and below the x nullline. which means that we are going to look at the ODE labeled A. When y equals 0, x prime is identically 0. But as y increases, as we go above the x-axis, x prime becomes negative. So we simply note that x prime is negative everywhere above the x-axis. What that means is our left-right flow will always be heading left. Now, if we look below the x-axis, again, looking at equation A, y becomes negative, making x prime positive. So the direction of flow is always going to be going right. Now, what about the y nullline? On this curve, the derivative y prime is identically 0. So what happens as we increase y and move above the curve? That is going to make our derivative positive. So above the curve, y prime is going to be positive. Even below the x-axis, y prime is still positive when we are above the curve. So in these regions, let's draw the direction of flow appropriately. For y prime positive, we draw an upward arrow. And by similar reasoning, we can see that inside the curve, in other words, underneath the curve, y prime is going to be negative. And so direction of flow is down. One last thing that's helpful is to look at how solution trajectories are going to cross each one of these nullines. Now, along the x nullline, there is no left-right movement. So only up-down movement is possible. So looking to the right of the equilibrium point 1, 0, we notice that y prime is positive in all of those regions. So we can safely say that solution trajectories are going to cross going straight up. And that's going to be true both to the right of the curve and to the left of the curve. Inside the curve, solution trajectories are going to be moving straight down. Now on the y nullline, there is no up-down movement, only left-right. So here we look at the direction of flow for x. Above the x-axis, the direction of flow is always moving left. And below the x-axis, the direction of flow is moving right. What does this imply then for potential solution trajectories? Let's start in the lower right. Curves should be moving right and up, and as they cross the x-axis, they'll cross exactly vertically. Once they get into the upper right quadrant, they need to start moving left and up.
Solution curves that cross the y nullline are going to have to cross exactly horizontally.
And start moving left and down.
The flow trajectories will then continue and
cross vertically back down into the lower right quadrant. But some curves are going to cross out, and they have to cross
horizontally,
but then they need to start moving up. From the lower left quadrant, we have a similar kind of behavior. So what we're seeing is some interesting possible behavior emerging. The behavior around the right equilibrium point looks maybe a little spirally. Around the left equilibrium point kind of looks like a saddle point. After we get accustomed to thinking about how to create these phase diagrams, we are then going to talk about how do we formally analyze what is happening around every equilibrium point that we find in a nonlinear system like this. Okay, that's it for today. When we meet in class, we are going to do a lot more practice with phase portraits. See you then.